So, good afternoon, everyone. I think you have just had your lunch and you'll have to bear through this session. So, please hold on. Uh, what I will do is that, as a part of this presentation, I will take you through that what are the things in quantum solution, and we will start with the first question, that what it is that quantum is offering and why it is a discussion. So this actually comes from the limits we have reached in traditional computing, which is that you cannot keep on reducing the size of the transistors any further. You're already into the nanometer range. So now, on the other side of it, there is certain advantage which was developed in quantum mechanics, which led to the development of quantum computers. Now there is a very interesting relationship, which is like the way you represent a data in computing is that you have a bit representation which is 0 or 1, whereas there is a quantum analog called as quantum bit, which can represent 0 and 1 at the same time. It is the second part of the thing which makes it interesting, is that the power actually increases exponentially in proportion to the number of qubits, whereas in the traditional computing, there's a linear relationship. So the question is that quantum computers are not like going to solve everything, but they are efficient. It is efficient in certain problems, and whereas the classical computers actually are going to be doing a lot of the other stuffs otherwise. So it's not that quantum computers will replace everything. It's going to be a hybrid model where things can be accessed the other way high performance computing came. So quantum computers in general are suited for some of the optimization problems which Dr. Veni mentioned in some simulations. But the critical part is that what happens is that because of the advent of quantum computing and the quantum computers becoming more and more powerful, the threat of quantum hacking is real, and you have algorithms in place which will render today's encryption invalid. Now, something we can kind of take through something in the history. So in 1977, when RSA was first in place, it was said it will not be broken for the next 10,000 years. It was broken in less than 17 years in the year 1994. So what has happened since then is that the key size has got expanded, which Dr. Veni also mentioned. But even today, when we use RSA 2048, it is claimed that it will take about million years, but it is only for a classical computer. Quantum computers of something like 1 million, 10 million qubits, noisy quantum bits, can break it in real time. So what has happened because of this advent is that any data that you're looking at with about 5+ years of confidentiality is at risk. And the first victims are going to be government, banks, telecom operators, and data centers. This is the risk part of it. The second is that modern communication is designed in such a way that you cannot prevent data harvest. So data is harvested regularly, and you have no idea if what is happening to the data which you're sending on classical channels, right? So what we see is that without having quantum resilient encryption in place, there will be a collapse, and therefore it is the right thing to ensure that whatever methods we are using are resilient to both classical as well as quantum computers. This could be at software, hardware, both, right? So what we do is that we use quantum technologies to build quantum safe communication. So what we offer is that we offer solutions which are quantum resilient, and the security is not based on mathematical complexity. It is guarded by the laws of physics. And when you see that the systems that we have built are actually integrable with the existing infra. Now, this is what typically happens, that you actually need to have an encryption algorithm, a key which is being generated, and a channel to be shared. Now, with the solution in place, we can actually address all three problems, which is that your algorithm will be safe against both quantum as well as classical computers. Your keys are based on truly random number generators. We can talk about it later. The other part is that we are using fiber optic channel. What it means is that even before you release your data onto that channel, you can see if the line is safe. So now this is just a chart for comparative analysis, what happens conventionally versus what happens in quantum. So if there are two people, let's say typically it's Alice and Bob, but if they want to share, regularly what we do is that we have method to exchange the key over the internet, and then we can encrypt like we can share the symmetry key through RSA or any public key method, and then we can encrypt the data and share the data with the other party, and the other party can decrypt it. Whereas in which this is not quantum safe. Whereas on the other side, we have QKD, what is called as a quantum key distribution. What it does is that we can generate keys on demand, and where there will be a dedicated line, and then it can be used for encrypting your data, and the other party can get to know. Now, the advantage is that it is one of the methods, or I believe is the only method, which can generate keys on the go without having any trusted party in between. And the security is guaranteed by the laws of quantum physics. Therefore, no advancement in computing will have impacts on its security. And if you use something like one-time pad, then it's basically an unconditional security. Coming to the another point, which is not typically also appreciated, but then is very important, is that whenever you want to share your data onto that channel, any attempts which are being made onto a quantum channel, you can find out if someone is eavesdropping. Now, this is something where you can discard the keys on the go. So you can use a multiplexed QKD systems, and you can ensure that even when you're sharing your data, you know what is happening to the data channel. This is one of the big advantages of using QKD. And since this is an add-on technology, it actually integrates with your physical layer, so therefore no change. Of course, there are some versions in which some bit of change is required, but this is an add-on technology, and these are the advantages. So what we typically see is that this modeling of the security is based on infinite capability any eavesdropper would have, and will still be okay to use this system. And you can detect intrusion. So just to sum it up, this it's a bit exhaustive, but this is what we see is that in the near term we will have QKD linked networks, and as the PQC part, which my fellow panelist talked about, will also get integrated. So it's going to be more like a hybrid model, and strictly speaking, that QKD only helps in exchanging the keys, after which we use symmetry key methods to encrypt our data. So typically, this is how QKD system is deployed, where you have a quantum layer on which the keys are being exchanged, and then the keys are being managed, then used for your communication, right? So this is one of the most, as Dr. Veni also mentioned, that is being deployed across different geographies. China is leading a race where they have when they have 5,000 kilometers of quantum networks in place, in addition to the quantum satellites that is used between cities for communication. And the similar developments have been happening in Japan, in US, in Europe, and standards are being evolved. So this is one technology which is not just limited to lab, but is also being thoroughly used in different geographies. So with that, I probably will end, because we have 5-6 minutes. So thank you so much.